Have you ever picked up your smartphone or, I don't know, even just a simple rock and found yourself wondering, what is this really made of? I mean, we interact with the physical world constantly, but underneath it all, there's this incredible unseen story, right? Fundamental particles and forces shaping everything. Today, we're going to take a deep dive into the components of matter. We're drawing from a really fantastic chapter in Silberberg and Amateus's Chemistry, The Molecular Nature of Matter and Change. And our mission really is to cut through the dense parts of these core chemistry concepts, give you a clear, engaging shortcut to understanding the very foundations of everything around us, and importantly, no diagrams needed.
Indeed, and it's quite a journey, actually. We'll go from, ancient philosophical debates about these indivisible particles all the way to cutting-edge techniques, things like mass spectrometry, that precisely measure atomic structure today. We'll unpack how matter is classified, how its fundamental laws were discovered, and really how we've come to grasp its intricate atomic and, yes, subatomic architecture.
Okay, so let's start at the beginning then, maybe with a bit of that history. Because for centuries, people were speculating about what matter's basic nature was, right?
Absolutely.
You had the ancient Greeks, like Democritus, with this really radical idea of atomos, these like uncuttable particles. But then for nearly 2,000 years, Aristotle's idea of a continuous substance, something infinitely divisible, that kind of won out.
It did, yeah. It held sway for a very long time.
So how do we finally move past that? And what did those early ideas, like Robert Boyle talking about simple bodies in the 17th century, what did they evolve into?
Right, well, that's where we get our initial, and I'd say absolutely crucial, classifications. Fundamentally, all matter fits into one of three buckets: elements, compounds, or mixtures.
Mm.
The big shift was realizing that composition is key. So elements and compounds, we call those substances. Why? Because they have a fixed, unchanging makeup. Mixtures, on the other hand, well, they're variable. Their composition can change.
Okay, so substances have fixed recipes, mixtures don't. Got it. Let's break those down. Elements first.
Elements, exactly. They're our simplest building blocks. Each one is defined by its unique kind of atom. Think of them as the fundamental unbreakables, chemically speaking. Pure silicon in your computer chips, or the pure copper in electrical wiring. And some elements, like oxygen, actually exist as molecules. That's where two or more atoms of the same element are bound together, like O2.
Okay, simplest form, and then compounds.
Then we have compounds. These form when two or more different elements chemically bond together. They actually join in a chemical reaction. And what's really astonishing here, truly, is that a compound's properties are completely different from the elements that make it up.
That always blows my mind.
It's amazing, isn't it? Think about it.
Okay.
You take soft, silvery, highly reactive sodium metal,
Yeah.
and poisonous yellow-green chlorine gas.
Yeah.
And they combine to form white, crystalline sodium chloride, just common table salt, something totally different and essential for life.
That's incredible, and they always combine in the same way.
Always. That's the key. The elements in a compound are always present in fixed parts by mass. Why? Because each unit of the compound has a fixed number of atoms of each element. Ammonia, for instance, is always 14 parts nitrogen to 3 parts hydrogen by mass. And you can break compounds down, but only through chemical change, not physical.
Okay. Elements and compounds is the substances with fixed composition. What about the third category, mixtures?
Right, the mixtures. Here you have two or more substances, so elements or compounds, that are just physically intermingled. They're not chemically combined.
Like tossing salad ingredients together.
Exactly like that. And unlike compounds, their proportions can vary. Your salt water can be really salty or just a little salty. And crucially, the components in a mixture, they pretty much keep their individual properties.
Ah, so the salt still tastes salty, the water's still wet.
Precisely. Salt water still tastes salty. It's clear like water. And because they're only physically mixed, you can separate them using physical changes. Boiling the water off to leave the salt behind is a classic example.
Okay, this basic classification, elements, compounds, mixtures, based on composition and how things are combined, that makes a lot of sense. But you mentioned earlier, even before we had a solid atomic theory, chemists were noticing patterns, these mass laws.
Yes, these mass laws were absolutely critical. They were the pieces of the puzzle that just didn't fit with the old ideas and, frankly, demanded a new model of matter. First up, there's the law of mass conservation. This was articulated by Lavoisier back in the 18th century, and it's quite simple, really. The total mass of substances does not change during a chemical reaction. Matter cannot be created or destroyed.
So what goes in must come out, mass-wise.
Exactly. If you metabolize glucose, for example, 180 grams of glucose plus 192 grams of oxygen will yield exactly 372 grams of carbon dioxide plus 108 grams of water. The total mass is conserved.
Okay. No disappearing matter. What else?
Then there's the law of definite composition, or constant composition. This is that no matter where you get it from, a particular compound is always made of the same elements in the same fixed proportions by mass.
Like your salt example earlier.
Precisely. Or think about calcium carbonate. Whether it's in seashells or marble or coral reef, it's always 40% calcium, 12% carbon, and 48% oxygen by mass. Always. Doesn't matter the source.
That's a powerful idea for analysis.
Immensely powerful. If you know a sample of, say, pitchblende ore contains a certain percentage of uranium by mass, you can calculate exactly how much uranium is in any size sample of that ore because the ratio is fixed.
Okay, definite composition. And there was a third one.
Yes, the law of multiple proportions. This one's a little more subtle but really clever. It says if you have two elements, let's call them A and B, and they can combine to form more than one compound.
Like carbon and oxygen can make carbon monoxide and carbon dioxide?
Exactly like
Yeah.
Then if you look at the masses of element B that combine with a fixed mass of element A in those different compounds, those masses of B will relate to each other as a ratio of small whole numbers.
Whoa, okay, unpack that a bit.
Right. So take your example. Carbon monoxide, CO. For every gram of carbon, there's about 1.33 grams of oxygen. Now take carbon dioxide, CO2. For every gram of carbon, there's about 2.66 grams of oxygen.
Mm-hmm.
Now look at the ratio of those oxygen masses. 2.66 divided by 1.33. What do you get?
2.
Exactly. A perfect small whole number, 2 to 1. It's not some weird fraction. It's simple. This wasn't a coincidence. It happened again and again.
Okay, these laws, mass conservation, definite composition, multiple proportions, they're painting a picture of matter being made of discrete units with fixed properties, aren't they? It feels like someone needed to connect the dots.
You've hit it, exactly. And that someone was John Dalton. His atomic theory, proposed around 1808, was just a monumental breakthrough. He took all these observations, these laws, and synthesized them into a coherent model.
What were the key points of his theory?
Well, there were a few core postulates. First, all matter consists of atoms, these tiny, indivisible, indestructible units. That echoes Democritus, and it neatly explains mass conservation atoms just rearrange. Second, atoms of one element can't be changed into atoms of another element during chemical reactions, so no alchemy, they just recombine. Third, and this was a major new idea, atoms of a given element are identical in mass and properties, and they're different from atoms of any other element. And fourth, compounds result from the chemical combination of atoms of different elements in a specific ratio. And that directly explains definite composition, right? Fixed ratios of atoms mean fixed ratios of mass.
Wow. So his theory just elegantly tied everything together. Mass conservation because atoms aren't created or destroyed, just rearranged. Definite composition because compounds have fixed atom ratios.
Yeah.
And multiple proportion.
Because atoms combine in whole numbers. You can have one carbon with one oxygen, CO, or one carbon with two oxygens, CO2. That naturally leads to those small whole number mass ratios. It was incredibly powerful.
It really sounds like a complete picture. But, science never really stops, does it? Dalton's billiard ball atom, as elegant as it was, couldn't explain everything, like, say, electricity or why atoms bonded.
Precisely. The picture wasn't quite complete. Dalton's model was a huge leap, but the late 19th and early 20th centuries brought experiments that started to, well, crack that billiard ball open. They peered inside the atom.
And what was the first big crack?
The discovery of the electron. It started with experiments on cathode rays. Scientists were passing electricity through evacuated glass tubes and saw these rays coming from the negative electrode, the cathode. Crucially, these rays were deflected by magnetic and electric fields. That proved they were made of negatively charged particles. Then J.G. Thomson, in 1897, did brilliant work measuring the mass-to-charge ratio of these particles.
And what did he find?
He found they were incredibly light, less than 1,000th the mass of a hydrogen atom, which was the lightest atom known. This was revolutionary. It implied atoms themselves contained even smaller pieces.
So I bet that was hard for people to accept.
Oh, absolutely. Thomson himself was met with disbelief. The idea of an indivisible atom was deeply ingrained, but he discovered the electron. Then, a bit later, Robert Millikan performed his famous oil drop experiment. By suspending tiny charged oil droplets in an electric field, he managed to measure the fundamental charge of a single electron with amazing precision.
And combining that with Thomson's ratio?
They could calculate the electron's actual mass.
Yeah.
And it was minuscule, confirming Thomson's findings. So atoms definitely weren't indivisible.
Okay, so we have these tiny negative electrons. But atoms are neutral overall, so where's the positive charge? And where is most of the mass?
The next big question. Thomson proposed what's often called the plum pudding model, basically a diffuse sphere of positive charge with these negative electrons embedded in it, like plums in a pudding.
Sounds plausible. How did they test that?
Enter Ernest Rutherford and the famous gold foil experiment around 1910. This is one of the most pivotal experiments in science history. He took tiny positively charged particles, alpha particles, and fired them at a very thin sheet of gold foil.
What did the plum pudding model predict would happen?
It predicted that these alpha particles, being relatively heavy and fast, should mostly zip straight through the pudding, maybe with tiny deflections. Rutherford apparently likened it to firing bullets through tissue paper.
But that's not what happened, is it?
Not at all. The results were, frankly, astonishing. While most alpha particles did go straight through, a very small fraction were deflected at large angles. Some even bounced almost straight back.
Whoa.
Rutherford was famously stunned. He later said, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you."
That's a fantastic quote. So what did this bombshell result mean for the atom's structure?
It completely overturned the plum pudding model.
Huh?
Rutherford concluded that the atom must be mostly empty space. All the positive charge and almost all the mass had to be concentrated in an incredibly tiny, dense central region, which he called the nucleus.
So the alpha particles were bouncing off this tiny, dense positive core.
Exactly. This discovery eventually led to identifying the positive particles in the nucleus as protons. And then, a bit later, in 1932, James Chadwick discovered the neutron, another particle in the nucleus, similar in mass to the proton but with no charge. That accounted for the rest of the atom's mass.
Okay, so we've gone from billiard balls to plum pudding to this tiny nucleus with electrons orbiting somehow. That's a huge conceptual leap.
It truly is.
Yeah.
And if we jump to our modern understanding connecting all these pieces, an atom is an electrically neutral sphere. You've got the central nucleus packed with positive protons and neutral neutrons. And then surrounding this nucleus, moving rapidly, are the negative electrons. And the scale difference is just mind-boggling. An atom's overall diameter is maybe 10,000 to 100,000 times larger than its nucleus. Yet that tiny nucleus contains something like 99.97% of the atom's mass. It's incredibly dense.
You gave that Astrodome analogy earlier, the atom as the stadium, the nucleus as a P at the center, holding almost all the mass. That really helps visualize the emptiness.
It does, doesn't it? It highlights just how much of the atom is essentially this space occupied by the electrons.
So with protons, neutrons, and electrons, what actually defines which element an atom belongs to? Is it the number of protons?
Precisely. The atomic number, symbolized as Z, is simply the number of protons in the nucleus. This number uniquely defines an element. Every single carbon atom in the universe has 6 protons. Every oxygen atom has 8. Change that number, you change the element. Period.
Okay, Z is the element's ID. What about the mass?
That involves the neutrons too. The mass number, A, is the total number of protons plus neutrons in the nucleus. So A equals Z plus N, where N is the number of neutrons.
Right, and this leads to isotopes, doesn't it?
Exactly. Isotopes are atoms of the same element, meaning they have the same number of protons, same Z, but they have different numbers of neutrons. This means they have different mass numbers, A.
Like carbon-12 and carbon-14.
Perfect example. Both are carbon. Both have 6 protons. But carbon-12 has 6 neutrons, A12, while carbon-14 has 8 neutrons, A14. Chemically, they behave almost identically because chemical behavior is mostly determined by the electrons. And in a neutral atom, the number of electrons equals the number of protons.
So why isn't the atomic mass on the periodic table a nice whole number then, if it's just protons plus neutrons?
Good question. The number you see on the periodic table, the atomic mass, isn't the mass number of a single isotope. It's the weighted average of the masses of all the naturally occurring isotopes of that element, taking into account how abundant each isotope is in nature.
Okay, so it's an average reflecting the natural mix.
Exactly. And the standard unit for this, the atomic mass unit, EMU, or Dalton here, is defined as exactly 112th the mass of a single carbon-12 atom. These average masses and isotopic abundances are measured with incredible precision using mass spectrometry.
Mass spectrometry.
Yeah.
Sounds complex.
It's a fascinating technique. Basically, you ionize atoms, shoot them through magnetic or electric fields, and they get separated based on their mass-to-charge ratio. This lets you measure both the mass of each isotope and how much of it there is.
Okay, that makes sense. Now with, 118 known elements and their isotopes, keeping track must be a challenge. How did chemists organize all this information?
This is where one of the most powerful tools in all of science comes in, the periodic table of the elements. Dmitry Mendeleev gets a lot of credit for publishing the most successful early version back in 1871. He noticed that if you arranged elements by increasing atomic mass, elements with similar properties appeared at regular intervals or periods.
But the modern table is arranged slightly differently, right?
Yes, the modern table is arranged by increasing atomic number, Z, or the number of protons. This turned out to be the more fundamental organizing principle.
And how is it structured?
It's arranged in periods, which are the horizontal rows, and groups, which are the vertical columns. And this structure isn't just arbitrary. It reflects patterns in electron configurations, which dictates chemical behavior. We also broadly classify elements on the table. You have the metals dominating the large lower left portion, typically shiny solids, good conductors, malleable, ductile. Then the nonmetals in the smaller upper right, often gases or dull, brittle solids, poor conductors. And wedged between them are the metalloids or semimetals, showing intermediate properties.
And those groups, the columns, are important. I hear names like alkali metals or halogens.
Very important. Elements within the same group tend to have similar chemical properties because they have similar outer electron arrangements. So group 1, the alkali metals, are all very reactive metals. Group 17, the halogens, are reactive nonmetals. Group 18, the noble gases, are famously unreactive. Knowing the group tells you a lot about an element's personality, chemically speaking.
So the periodic table isn't just a list, it's predictive.
Absolutely indispensable. It organizes vast amounts of chemical information and predicts properties and reactivity trends.
Okay, so we have all these elements. Now, what's fascinating is that most of them don't just hang out alone, right? Except maybe those noble gases. Most elements seem to want to combine to form compounds. How does that actually happen? How do they stick together?
That's the realm of chemical bonding. And elements combine in two main ways, both fundamentally involving the electrons, particularly the outer electrons, of the interacting atoms. These interactions create the chemical bonds, the forces holding atoms together.
What's the first way?
The first way generally leads to ionic compounds. This typically happens when a metal reacts with a nonmetal. What occurs is an actual transfer of electrons. The metal atom tends to lose one or more electrons, becoming a positively charged ion, which we call a cation. The nonmetal atom tends to gain those electrons, becoming a negatively charged ion, an anion.
Like sodium losing an electron and chlorine gaining one.
Exactly. Sodium becomes Na+, fluorine becomes Cl, and then what happens? Opposite charges attract. These positive Na+ cations and negative Cl anions are strongly attracted to each other, forming a repeating, three-dimensional crystal lattice structure that's your table salt crystal.
So it's not like individual NaCl molecules floating around?
Not in the solid state, no. It's a vast network, an array of ions held together by electrostatic attraction. We describe the strength of this attraction using Coulomb's law, stronger attraction, with higher charges and shorter distances between the ions.
And can we predict what ions elements will form?
For many main group elements, yes. There's a strong tendency for atoms to lose or gain electrons to achieve the same number of electrons as the nearest noble gas, because that configuration is very stable. So group 1 metals tend to lose one electron to form 1+ ions. Group 17 halogens tend to gain one electron to form 1 ions.
Okay, that's ionic bonding, electron transfer between metals and nonmetals. What's the other main way atoms bond?
The second way leads to covalent substances, and this usually happens between two nonmetals. Instead of a transfer, here atoms share electrons. They form a covalent bond, which is essentially a pair of electrons that is mutually attracted by the nuclei of both atoms involved. This sharing holds the atoms together.
Can you give an example?
Sure. Two hydrogen atoms can each share their single electron with the other, forming a stable hydrogen molecule, H2. Water, H2O is another classic example, with oxygen sharing electrons with two hydrogen atoms, or hydrogen fluoride, HF.
And unlike ionic compounds, these often exist as distinct units.
Yes, that's a key distinction. Most covalent substances exist as discrete molecules, individual, self-contained units of bonded atoms, like an H2O molecule. Although, just to add a little complexity, you can also have polyatomic ions. These are interesting because they're groups of atoms, like the carbonate ion CO32, where the carbon and oxygens are covalently bonded to each other, but the entire group carries an overall net charge, in this case 2. These charged groups then behave like single ions in forming ionic compounds.
Okay, wow. Ionic transfer, covalent sharing, polyatomic ions. It feels like chemistry needs its own language just to keep track of all these combinations. How do chemists name and write formulas for all this stuff?
An excellent point. Consistency is crucial. We use chemical formulas element symbols with numerical subscripts to show the exact type and number of atoms in the smallest unit of a substance. For ionic compounds, we call this smallest ratio the formula unit.
Are there general rules?
Yes. Generally, the cation, positive part, comes first in the name and formula, followed by the anion, negative part. And a subscript 1 is always implied, never written.
Okay, what about naming simple ionic compounds, say a metal and a nonmetal?
If the metal typically forms only one type of ion, like calcium, K2 plus ion, or zinc, Zn2 plus, it's simple. Just the metal name plus the nonmetal root name with an odd suffix. So Cab2 is calcium bromide, ZNO is zinc oxide. You just figure out the ions and balance the charge to get the simplest whole number ratio for the formula.
But some metals, like iron, can form different charges, right?
Yeah.
F2 plus and F3 plus stem.
Exactly. For metals that can form more than one type of ion, often transition metals, we need to specify the charge. We use the metal name followed by a Roman numeral in parentheses indicating the positive charge, then the nonmetal root plus "ide." So FCl3, where iron is 3 plus I, is named iron 3 chloride. FCl2, where iron is 2 plus I, is iron 2 chloride.
Got it. Roman numerals for ambiguity. What about those polyatomic ions?
You just use the specific name of the polyatomic ion.
Yeah.
For example, KNO3 contains the K plus ion and the nitrate ion, NO3, so it's a potassium nitrate. AOH2 is barium hydroxide. Notice the parentheses around OH. You need them if there's more than one polyatomic ion unit. And there are naming patterns for related polyatomic ions, especially oxygen-containing ones called oxoanions. Suffixes like ate, more oxygen, and ite, less oxygen, and sometimes prefixes like per, most oxygen, and hypo, like oxygen, help distinguish them, like perchlorate, ClO4, chlorate, ClO3, chlorite, ClO2, and hypochlorite, ClO.
That sounds like something you just have to memorize over time.
It does take practice, yes. There are also rules for naming acids compounds that produce H plus ions in water. Binary acids, H plus nonmetal, use hydro prefix and ic acid suffix, like hydrochloric acid, HCl. Oxoacids, H plus oxoanion, are named based on the anion. 8 anions become ic acids, nitrate nitric acid, HNO3, and ic anions become ic acids, nitrite, nitrous acid, HNO2.
Okay, that covers ionic compounds and acids. What about the covalent ones between two nonmetals?
For binary covalent compounds, we use Greek numerical prefixes, mono, di, tri, tetra, penta, etc., to indicate the number of atoms of each element. The first element usually keeps its name, unless there's only one, then motto is often dropped, and the second element gets the iide suffix.
Like carbon dioxide, di for 2 oxygens.
Exactly. CO2 is carbon dioxide, N2O4 is dinitrogen tetroxide, SO2 is sulfur dioxide, PCl5 is phosphorus pentachloride. The prefixes tell you the formula directly.
And I guess we can calculate masses from these formulas too.
Absolutely. The molecular mass for molecules, or formula mass for ionic compounds, is just the sum of the atomic masses from the periodic table of all the atoms shown in the chemical formula.
So with all these formulas and names, how do chemists actually, see these molecules that are way too small to observe directly?
Great question. We rely on various models because the formula itself, like H2O, only tells you the what and how many, not the how. A structural formula uses lines to show which atoms are bonded together. But to get a sense of the three-dimensional shape, we use physical or computational models. Ball and stick models show atoms as spheres and bonds as sticks. They're good for seeing bond angles clearly, but they kind of exaggerate the distances between atoms. Space-filling models, on the other hand, represent atoms as spheres scaled to their actual relative sizes and show how they overlap in bonds. These give a much better sense of the molecule's actual volume and surface, though you don't explicitly see the bonds. They're crucial for visualizing really large, complex molecules like proteins or DNA.
Okay, so we've built up from atoms to elements, compounds, bonding, naming. But you mentioned earlier, in the real world, stuff is rarely pure. It's usually mixtures.
That's right. Most of what you encounter every single day, the air you breathe, the oceans, food, rocks, alloys, they're all complex mixtures. And we classify these into two main types.
Heterogeneous and homogeneous.
Exactly. A heterogeneous mixture is one where you can actually see different parts or boundaries.
Yeah.
Its composition is not uniform throughout. Think of granite rock with its different mineral grains or oil and vinegar dressing. Even milk or blood, which look uniform to the naked eye, are heterogeneous. Under a microscope, you see fat globules or blood cells suspended.
And homogeneous.
A homogeneous mixture, which we also call a solution, has no visible boundaries. The components are mixed right down to the individual atom, ion, or molecule level. They're uniformly intermingled. Salt water is a classic liquid solution. Air is a gaseous solution. Alloys like brass or steel are solid solutions.
And the key difference, again, between mixtures and compounds.
Remember, mixtures have variable proportions. You can make salt water saltier. Their components retain their individual properties. Salt is still salty. Iron filings are still magnetic. And, crucially, mixtures can be separated by physical changes, techniques that don't alter the chemical identity of the components. Compounds require chemical reactions to break them down.
Right, like you can use a magnet to pull iron out of a mixture with sulfur, but once they react to form iron sulfide, the magnet won't work anymore.
Precisely. The iron's properties have changed chemically.
So what are some of these physical separation methods?
Chemists have a whole toolkit, exploiting differences in physical properties. Filtration separates solids from liquids based on particle size, think coffee filters. Crystallization separates dissolved solids based on differences in solubility, often by dissolving an impure solid in a hot solvent and letting the pure substance crystallize out as it cools. Distillation is great for separating liquids with different boiling points. You boil the mixture, the component that turns into gas more easily, the more volatile one, vaporizes first, then you condense it back to liquid elsewhere.
Like making distilled water.
Exactly. Or separating ethanol from fermented mash. And then there's chromatography, a really powerful set of techniques. It separates components based on how differently they distribute themselves between a stationary phase, like a solid or a viscous liquid, and a mobile phase, a liquid or gas that flows over through the stationary phase.
Hmm.
Components that interact less strongly with the stationary phase move faster and separate out.
Wow, quite a range of techniques just based on physical properties.
It's incredibly useful for purifying substances and analyzing complex mixtures.
So let's recap this whole journey. We've gone from the earliest philosophical ideas of atomos through those crucial mass laws, Dalton's unifying atomic theory, the discovery of electrons, protons, neutrons, the nuclear model.
Then understanding isotopes, the periodic tables organization, the two main types of chemical bonding, ionic and covalent, the systems for naming, and formulas.
And finally, distinguishing compounds from mixtures and the physical methods we use to separate those mixtures. It's quite a landscape we've covered.
It really highlights how beautifully the puzzle pieces fit together in chemistry, doesn't it? From the absolute smallest scale of the nucleus right up to the macroscopic mixtures we see every day. It shows this amazing progression from just observing to understanding to predicting how matter behaves.
Hopefully this deep dive has given you listening some serious aha moments, maybe demystified some of those terms, and provided a clearer roadmap for understanding these fundamental building blocks. You know, the next time you see a chemical formula or hear about an element on the periodic table, maybe you'll have a new appreciation for the incredible science packed into it.
And perhaps it sparks a question for you, the listener. Now that you have a grasp of these basic components, atoms, bonds, molecules, mixtures, what other mysteries of matter, maybe something you encounter daily or something more exotic, are you now curious to explore further?
That's a great thought to end on. Thank you so much for joining us on this deep dive into the components of matter. Keep exploring, keep asking questions, and definitely stay curious.